Hi, Assalamualaikum. Welcome back to my channel, Physics Form 4 KSSM. Today we continue to discuss on topic chapter 3, Gravitation. In this video, I will discuss 3.1, Newton's Law of Universal Gravitation, which I will explain the Newton's Law of Universal Gravitation. So this topic of gravitation is an interesting topic that discusses about universe. Discuss about how satellite able to orbit the Earth and how Earth able to orbit the Sun. And you can see here a lot of satellites able to orbit around the Sun, around the Earth, and also other planets. The idea of gravitation actually studied by Isaac Newton. He observed about an apple that fall to the ground. Isaac Newton realized that the motion of a falling apple and the motion of the moon were both actually the same motion, caused by the same force that called gravitational force. He observed that the apple fall down to the ground due to a force that pulled the apple towards the center of the Earth, gravitational force. Same thing, the moon and the planets. Motion of Earth, the moons and the planet. So you can see the moon orbiting the Earth. How can it maintain the motion orbiting the Earth? There must be a force that hold it so that it will maintain the orbits. So according to Isaac Newton, these two situations is caused by the same force, gravitational force. The Newton's idea was that gravity was a universal force acting between any two objects. Not only the case of apple and the Earth just now. We can discuss about other planets, Mars, Venus, Mercury, Earth, that stay in an orbit. The moon that orbiting the Earth. So it means when we discuss about two objects, there is a force that acts between the two objects. That one is the Newton's idea. Okay, let's look at this situation. At the Earth's surface, Newton knew that gravitational force on the apple equals to the apple's weight, mg, where g equals to 9.81 meter-second to the power -2. So for this apple, there is gravitational pull that acts downward that we call weight of the apple. And we can calculate the weight as W equals to mg. Newton's law of universal gravitation that produced by Isaac Newton conclude that gravitational force is directly proportional to the product of masses of both objects. And the gravitational force is inversely proportional to the square of distance between the centers of the two objects. When we discuss two objects like this, body 1 and body 2, distance between centers of the two objects is r. Mass of the first body is m1, mass of the second body is m2. According to Newton's law of universal gravitation, there will be gravitational force that acts between these two objects. So from Newton's law of universal gravitation, we can have this relationship. F directly proportional to m1 times m2, and F directly proportional to 1 over r squared. Combining these two relationships, we get F is directly proportional to m1 times m2 divided by r squared. So actually, this relationship is discussed by Newton's law of universal gravitation. Now we try to produce formula. In symbols, Newton's law of universal gravitation is Fg directly proportional to m1 times m2 divided by r squared, and also can be written in form of equation as F equals to G m1 m2 divided by r squared. What is this capital G? This capital G is a constant. We call it universal gravitational constant. Value of G is equals to 6.67 times 10 to the power -11 Newton meter squared per kilogram squared. So this value will be given, no need to memorize this value, but you must know how to use this formula later in problem solving. Based on the formula, we can discuss about factors that affect gravitational force F. Based on the formula, we can see clearly the two factors are mass of the two bodies. Means the larger the mass of two bodies, the larger the gravitational force, or vice versa. And then the distance from the centers of the two bodies are gravitational force decreases when distance between two bodies increases. Meaning if the two objects are closer, the gravitational force act between the two objects is larger compared to if the two objects are further away from each other. Let's look at example 1, how to use the formula Newton's law of gravitation. Calculate the gravitational force between durian and the earth. Let's say there's a durian falling and then fall to the ground, meaning towards the earth. Mass of durian is 2 kg. Mass of the earth equals to 5.97 times 10 to the power 24 kg. Distance between center of the durian and center of the earth equals to 6.37 times 10 to the power 6 meter. So what is gravitational force between durian and the earth? So F equals to G mm divided by R squared. So just substitute the value. Okay. Universal gravitation constant. So multiply m1, m2 divided by R squared. So we get 19.63 Newton. So this 19.63 Newton is a force that acts on earth and also acts on durian. Okay. If you look at the value of force here, what do you think about the movement of the earth? Does the earth move or not? The durian, of course, it will move. You can calculate using formula F equals to ma. Okay, this is the gravitational force. So you can get acceleration towards the earth about 9.81. So meaning the durian accelerating or free fall towards the center of the earth. How about the earth? If we use the formula F equals to ma to calculate acceleration of the earth, with this value of larger mass of the earth, you will get the value of acceleration is about 0 or very, very small until you can see 0. That's why earth does not move. Okay. Example 2, a rocket at a launching pad experiences gravitational force of 4.98 times 10 to the power 5 Newton. What is the mass of the rocket? Mass of the earth given. Distance between center of the earth and center of rocket also given. From the formula of gravitational force, we get G m1 m2 divided by R squared. Assume that mass of rocket equals to m2. You substitute the value of F, the value of G, m1 is mass of the earth, and m2, mass of the rocket. Okay, the distance between centers, 6.37 times 10 to the power 6 squared. Okay, you solve this one, you will get m2 equals to 5.07 times 10 to the power 4 kilogram. Be careful when you use calculator involving larger value like this. Sometimes there is a careless mistake. So m2, you get the value. So this is mass of rocket. Okay, now we want to relate between G and small g, gravitational acceleration G on the surface of the earth and universal gravitational constant G. According to Isaac Newton, gravitational force acts on the object that falls. Actually, it's the same force that acts when an object orbiting the earth. Okay, which one is discussed in the Newton's universal law of gravitation. So for the first part here, gravitational force causes object to fall with acceleration g. Based on the Newton's second law of motion, so we get F equals to mg. And then gravitational force pulls object to the center of the earth, meaning earth pull the object pull the earth. Okay, and then we get F equals to g mm divided by R squared. The capital M is mass of the earth. The small m is mass of the object. and r is distance between centers of the object and Earth. Okay, so because of, according to Isaac Newton, the forces that act actually are the same force, then we can write this relationship. mg equals to gmm divided by r squared. The small m, you can cancel it. So you will get gravitational acceleration equals to gm divided by r squared. Meaning, from this formula, the value of gravitational acceleration just depends on distance between centers of the two objects squared, because the value of g and capital M are constant. G is universal constant, m is mass of the Earth, which is also constant. So based on that formula, the factors that influence the value of gravitational acceleration is only distance between center of the Earth and center of the object r. If r is longer, then g is smaller. You can see from here, g inversely proportional to r squared. Okay. If r is longer, then g is smaller. Okay. Now we look at a graph of g against r, shows the value of g with different values of r. So we have this graph, g against r. So at the point 0 here, or the center of the planet, if we discuss about Earth, meaning center of the Earth, g is equals to 0. From the center of the Earth to the surface of the Earth, the distance, we call it a radius of the Earth. We discuss about Earth. Okay, so at the surface of the Earth, the gravitational acceleration will become g equals to gm divided by r squared, because from center of the Earth to the surface is capital R, which is a radius of the Earth. And then when distance between centers increases to 2r and 3r, we can see the value of g drop or decreases. So we can say from here, this graph, g is inversely proportional to r squared. So this one is the graph. This one is the graph that used based on the formula. So when the object is far from the Earth, the value of gravitational acceleration decreases. Okay, when go to the moon, it becomes 1/6 from the, as compared to gravitational acceleration on the Earth. Okay, so this is the graph that shows how value of g change based on changing in value of r. So from here we can see here, value of g is directly proportional to distance from center of the Earth, r less than capital R, meaning any distance less than radius of the Earth, the value of g is directly proportional, straight line, pass through origin. And then after r, g is inversely proportional to the square of distance from center of the Earth for r more or equals to capital R, meaning the value of gravitational acceleration, 9.81, is the highest value on the surface of the Earth. When go further away from the Earth, the value will decrease. Okay, let's try to determine the value of g. Defined from this diagram, h is height of the satellite from the surface of the Earth. This is satellite orbiting the Earth. Radius of the Earth, capital R. This is radius of the Earth. Small r, distance of satellite from the center of the Earth, radius of orbit. Meaning from center to center between two objects, satellite and Earth, is small r. Satellite is at height h from the surface of the Earth, thus distance from the center of the Earth equals to radius of the Earth plus h, or height. So that one will equals to small r. So we get r equals to capital R plus h. So from here, the gravitational acceleration g equals to gm divided by r squared. R equals to radius of the Earth plus height. So we just substitute here squared. So this is the formula used for gravitational acceleration according to the distance between object and the Earth. Distance from the center of the Earth r equals to radius of the Earth, capital R. So gravitational acceleration on the surface of the Earth, G equals to gm divided by r squared. So if you have the value of G, the gravitational constant, you have the mass of the Earth, and you have radius of the Earth, then you can determine gravitational acceleration on the surface of the Earth. Let's look at example 1, how to use the formula. Mass of the Earth given, radius of the Earth is given. Calculate gravitational acceleration on the surface of the Earth. So be careful when you read the question. Okay, so now the formula, G equals to gm divided by r squared. Because of at the surface, then the distance between centers of the object equals to radius of the Earth. Okay, r, small r equals to capital R. So you substitute the value of G, value of m and r, and then you will get G equals to 9.81 meter second to the power negative 2. So this is the value of G, okay, on the surface of the Earth. Example 3, a radar imaging satellite orbits around the Earth at height 480 km. What is the value of gravitational acceleration at position of satellite? So all the values are given: G, mass of the Earth, radius of the Earth. Height of the orbit, 480 km. So you convert to meter. Use the formula G equals to gm divided by r plus h squared. Because satellite is certain height h. So you need to add r plus h. Okay, unit must be the same. If here is meter, then here also meter. Because the final unit also in meter, second to the power negative 2. So you solve this one, you will get G equals to 8.49 meter second to the power negative 2. You can see satellite is further from the center of the Earth, or from the surface of the Earth. Thus the value of G is smaller than 9.81. The importance of knowing the value of gravitational acceleration. So based on the formula G equals to gm divided by r squared, we know that the only factors that affect value of G is distance between centers of two objects or two bodies. So we can calculate the value of small g by using that formula. So therefore, this formula can be used to calculate gravitational acceleration on the surface of other bodies such as planets, moon, and sun. Knowledge on the value of gravitational acceleration plays an important role in space exploration and continuity of life. For example, if astronomy go to the moon, okay, they know the value of gravitational acceleration on the moon and how long the astronomy will able to be there. So that one they must know the value of gravitational acceleration on the moon or other planet. So you can see the effects of gravity on growth of humans. Effects of high gravity. The first one, difference in density. Density increases. Bone fragility or seldom happens. Size of lungs compress. Blood circulatory system will cause heart pumps harder. Blood pressure will increase. And muscular system will become stronger. This one is due to high gravity. Effect of low gravity is immune system is weaker, skin becomes thinner, vision deteriorates, height increases almost 2 inches, anxiety, face swelling and legs become smaller, space sickness, seasickness or car sickness, bones become less dense. So all this will affect health of the astronomer. So it's better for them to know the value of small g before explore the universe, especially when go near to the black hole, for example, or away from the Earth. Okay, that's all my video today. So I hope you understand about the Newton's law of gravitation. So I will continue in the next topic, 3.1 part 2. Thank you for watching. Bye.